Welcome to A-Level and AP Physics, a place where you can improve your understanding of physics with confidence. In today's lesson, we will talk about AC and rectification from Cambridge A2 Physics. And in this video, we will only focus on past paper questions. If you are struggling with past paper questions and you don't know how to answer them, then watch this video carefully to improve your conceptual understanding and to get ready for coming exams. This question is about ideal transformer. As you can see here, number of turns on the primary coil are given to us. We have 5000 turns on the primary coil and primary voltage is given. Its RMS value is given and secondary voltage is also given, but its value is peak value. Peak value of secondary voltage is given. What we need to find out, we need to find the number of turns on the secondary coil. Now, how we can answer this? Let's try to understand a little bit about transformer first of all, and then try to answer this. This is our iron core, and let's say here is primary coil. So this is primary coil. So here is primary power source, and we can say its voltage is VP, and number of turns on this one we can say NP. Here is our secondary coil. Secondary coil, let's say this is the output. We can say the output will be VS and this will be NS. Number of turns on secondary coil. Now we understand is a very simple relationship that VP over VS is equal to NP over NS. So in this case we need to find NS, so simply we can say that this will be VP NP divided by VP. So we just need to plug in values, but only problem in this question is that one value is RMS value and one is peak value. So you can see here this is VP. So one value is RMS. I can simply say this is RMS value, and the other one is the peak value. For VS, we can also label like this. We have one value can be RMS, another value we can also calculate peak value. But what we need to plug in here? So very simple principle. If we are using RMS value for the primary voltage, we also need to use the RMS value for secondary voltage. So RMS we need to use. Otherwise, if we are using the peak value, of primary voltage, we also need to use the peak value of secondary voltage. So this is the only point what we need to understand, and then we can find our final answer. So this is how we can find our final answer. So just need to plug in values, that's all. And so here I have calculated for you. So you can see here, first of all, in this question, I have converted the peak value. So this is the peak value of secondary voltage. I have converted into RMS value, means I just divided peak value. If you are not clear about this concept, this is from alternating current AC chapter. So this is simply means V peak. The peak value you have to divide it by root of 2, and then we just plug in values. So our final answer for this part is 138 turns on secondary coil. Here is our part B, and part B simply we need to complete this rectifier circuit. As you can see, this is given, but this is incomplete. We have to complete this one. For part A, simply we need to use diode symbols and we need to complete this. But one thing more we need to keep in mind is that terminal A of the resistor is positive with respect to terminal B. What exactly it means? It simply means that current is entering from A. A is positive, it simply means the current has to enter from A side. So we can say this will be positive and this will be negative. For part B2, simply we need to use symbol for capacitor across the resistor to reduce the ripples in the potential difference. Simply, we need to complete the circuit using symbols for diodes and symbols for capacitor. So let me show you the answer first of all, and then I will explain to you this. So as you can see here, I have already drawn this circuit for you. So you can see the capacitor is connected here. So this is a typical question. Always you have to connect capacitor across resistor to reduce ripples. So we can say the purpose of this one is to reduce ripples. Next slide we will see more about ripples, or we often call this one smoothing. So it's the same meaning. So you can see here, if you look at these diodes, you will see kind of a similarity. For example, at this point, if we see, you see these diodes, they are converging to this end. And these two diodes, they are also converging to this end. So the side where they converge, that is connected with positive side. This is connected with positive side. And so I can say this side where these diodes converge, we connect this one with positive, and the other opposite end we connect with negative. And the remaining two terminals, they are connected with power supply. So this is the idea you need to understand. If you understand this one, then it's very easy to complete rectifier circuit. Means where they connect that side with positive. That's all. Other side with negative, and remaining two terminals with power supply. Let me explain to you a little bit more about bridge rectifier circuit, how to sketch them. So as you can see here, we have the next circuit here. In this circuit, if you look at this one, this side, if we start from here, these diodes, they are converging to this end. So simply you can draw these arrows like this. You can see they are converging at this side, at this end. So this end has to be connected with positive. So here it is connected with positive, means the current is entering from this side. If this one is resistor, so the current will enter from this side. And the other side we have to connect with negative. As you can see here, we have connected with negative. So this is how you need to sketch. And the remaining two terminals we have to connect with power supply. So as you can see here, we have connected with power supply. So this is the main idea, how to sketch bridge rectifier circuit. So let's look at some more examples now, so you can understand this concept even better. As you can see here, in this case again we have 4 diodes and there is one capacitor. So if you look at these diodes, how they're connected in bridge rectifier circuit, so this is called bridge rectifier circuit. So let me write down here if you're not clear about its name. So this is bridge rectifier, and we use this one for full wave rectification. So this is used for full wave rectification. So full wave rectification. So if you look at these two diodes, you can see they are converging to this side, this end, and these two, they're also converging to this end. So this end has to be connected with positive. As you can see here, in this case, this is connected with positive. And the other side has to be connected with negative, as you can see here. And the remaining two terminals has to be connected with power supply, as you can see this. So this is how we can sketch. For part C, as you can see here, it is given to us how the potential difference across the resistor is changing with time. So we have potential difference on y-axis and time is on x-axis. For C1, simply we need to state the interval of time when the capacitor is charging. From here, as you can see, the potential difference across the resistor is decreasing in this interval of time, or we can say here. So in this interval of time, as the potential difference across resistor is decreasing, we can say capacitor is discharging here. And if you look at the next interval of time, you can see the potential difference is increasing. So in this interval of time, the capacitor will charge. Capacitor will charge. So this is what we need to state. So simply we can say the capacitor is charging between T1 and T2. And also here we can say capacitor is discharging, here capacitor is charging, and here again it is discharging, and here is charging, and again discharging, and so on. So the time interval from T1 to T2. So this is answer. This is how simply we can answer this question. So here is our answer. And also this circuit is coming from part B. So let's move on to C2 now. For C2, the resistance of the resistor is double, mean we increase the resistance of this resistor. And now we need to sketch the variation with time t of potential difference V across the resistor, mean how potential difference across resistor will change if we increase its resistance. For this one, we need to understand something we call is a time constant, and time constant is equal to RC. So it means if we increase the resistance of the circuit, the time constant will increase. If the time constant increase, it simply, so it will take longer time. So simply we can say it will take longer time to discharge. Longer time to discharge. Another way we can also say it will discharge slowly, mean its potential difference will decrease slowly, discharge slowly. So this is the point what you need to understand. If we have understanding of this one, then we can sketch. So let's try to answer this one now, how we can sketch. So here is our answer. As you can see here, now I have sketched for you. You can see when the time constant is greater, means it discharges slowly. The potential difference also will decrease slowly across capacitor. As you can see, this value is greater than the previous value. It means this is discharging slowly. Discharge slowly. And this is true for all the values. If you compare these 2 points, you can see potential difference is greater. If you compare this point, potential difference is also greater if we increase the resistance of resistor. So this is how we can answer this question. And this question is kind of typical question, very common in A2 physics. I hope you have better understanding about this type of questions now. Welcome to A-Level and AP Physics, a place where you can improve your understanding of physics with confidence. In today's lesson, we will talk about AC and rectification past paper question from Cambridge A2 Physics. In this video, we will discuss how to calculate RMS value from a given equation, and also we will discuss how to calculate angular frequency. At the end of the video, we will also talk about why there is a large current in a circuit if a capacitor is connected across the terminals of a power supply. First of all, let's try to understand what is given to us. For this question, part A, it is given to us that the RMS value is equal to 14 volts and the frequency is equal to 750 hertz. And this equation is given to us. With the help of this equation, we can find the value of V at any given time. We can also write down like this. So V as a function of time is equal to V naught sine omega t. Sine omega t. So this V naught is the peak value of voltage. We can say this is the peak value. And this is voltage at any time. We can find if we have the value of time. So at any given time, we can find value of voltage at any given time. Now, what part A is asking us? Part A is simply asking us, we need to find the value, peak value of voltage. So peak value, this is quite straightforward one. So Vrms is equal to peak value divided by root of 2, and then from here we can find value of peak value. As RMS value is already given to us, this is equal to 14. So simply in this case the peak value will be equal to root of 2. We just need to multiply with given value of RMS, and that will be our final answer. So in this case our final answer will be 19.8 volts. So this is our final answer. For our second part, simply we need to calculate value of omega, and quite straightforward one. You just need to remember the basic formula. Even you can also recall from simple harmonic motion. Omega simply is equal to 2 pi f, and as you can see here, the value of frequency is already given to us, that is equal to 750 hertz. Just plug in these values and we can get our final answer. So in this case this is 2 pi. We just need to multiply with 750 hertz. If you multiply, our final answer is 4700. So simply we can say 4700 radians per second. So this is our final answer. For part B, a capacitor with a large capacitance is connected across the terminals of the power supply. We need to suggest and explain why there is a large current in the circuit. First of all, let's try to sketch based on given information. So it is given to us there is a power supply and there is also one capacitor that is connected across power supply, as you can see here. We can also attach one resistor across this capacitor, so this will be used for discharging. So let's say this is position A and this one is B. When we move this switch to A, capacitor will charge. So this one is a capacitor, this is a resistor. And when we move this to B, capacitor will discharge. We also need to understand that a capacitor can charge and discharge around 1000 times per second, even more than 1000 times per second. It means time taken for a capacitor to charge and discharge is very, very short time. Next thing what we need to understand is that Q is equal to CV. If the capacitance of a capacitor is large, it means for the same potential difference across its plates, it can store a large amount of charge. Next thing what we need to understand is the relationship between I, Q and T. If the Q is large, it means I will be large. If time is short, I will be even larger. So this is what we need to understand. If we understand these points, we write these 3 points, we will get full marks. Now let's try to write the final answer. So here is our final answer. Let me highlight what I have written for you. First thing I have written, capacitance is the ratio of Q over V. And second, if capacitance is large, it means it will store more charge. And next thing I have explained to you, a capacitor can charge and discharge very quickly. It means a large amount of charge in a very short time. So it means there is a large current from the power supply. So that's all. This is what we need to answer. Welcome to A-Level and AP Physics, a place where you can improve your understanding of physics with confidence. In today's lesson, we will talk about AC and rectification past paper question from Cambridge A2 Physics. This is our third video on this topic. In this video, I will explain you how to calculate mean value and how to calculate RMS value. At the end of the video, we will also talk about energy dissipated in a circuit. Here is our first question, and for this question, current against time is given to us. We need to be just a little careful because the time is on x-axis and time is in milliseconds. It is not in seconds. What we need to find, simply we need to find the frequency of the current. So this is quite straightforward one. Simply we need to find time period, and 1 over time period is equal to frequency. So first of all, let's try to find the time period. As you can see here, I already labeled this time. So time here is 2.5 and time here is equal to 17.5 seconds. So we can calculate the time for one complete cycle. Simply means that time taken will be equal to time period. Simply we need to just subtract these two numbers, or simply you can say these two values. So here is our final answer. So this is how we have calculated the time period. So this is time period and this is equal to 15 milliseconds, and frequency is equal to 1 over t. So this is our final answer. So this is frequency. Here is our part B. For part B, simply we need to calculate the mean current. It simply means that we need to take the positive value of current and also we need to take the negative value of current. We just need to add these two values and divide by 2. That will be mean current. So how we can calculate? So here you can see here I have already done for you. So this is positive value of peak current and this is negative value of peak current. We just added these two and divided by 2 because we need to calculate the mean value. And our final answer is 0. And this is true for any sine curve. For part C, simply we need to calculate RMS value. Means IRMS we need to calculate, and IRMS simply we can say is equal to IRMS. This is equal to peak value of current divided by root of 2. In this case, peak value we already have. As you can see here, this is the peak value. If you are not clear, you can also find from here. This is equal to 0.75 and we just need to divide by root of 2 and our final answer will be 0.53. So this is our final answer. For this part, we need to calculate the energy dissipated by the resistor, and the time is given to us. Time is from t is equal to 0 to t is equal to 30 milliseconds, and resistance is also given to us and current is also given. But for current, actually we have 3 different values. Those are given to us. The first value is mean value and the mean value is equal to 0. The second one is the peak value and the third one is the RMS value. So which value of current we have to use to calculate energy dissipated by the resistor? First of all, mean value is given. This is I is equal to 0 and the peak value is only at certain period of time. This is value is not constant, so we cannot use that value. But for IRMS, we need to understand IRMS actually is equal to IDC, direct current, for example, for a constant value. So if you need to calculate the energy dissipated, we simply need to use IRMS. We should not use I peak. We cannot use I mean. So let's try to calculate energy dissipated now. So energy simply is equal to I square RT. So we have time, we have resistance, and this value has to be IRMS. Now we just need to plug in values. The IRMS we have calculated, that was equal to 0.53. This value we have just calculated in part C, and the resistance is given to us that was equal to 450 ohms, and the time is 30 milliseconds. So we just need to simplify this and we will get our final answer. So in this case, final value of energy is equal to 3.8 joules. So this is our final answer. The concept you need to understand from here is that IRMS you need to use when you need to calculate the power or energy dissipated by a resistor. Welcome to A-Level and AP Physics, a place where you can improve your understanding of physics with confidence. In today's lesson, we will focus on AC and rectification from Cambridge A2 Physics. In this video, our main focus will be on bridge rectifier circuit, a very important topic from this chapter. Here we have a bridge rectifier circuit. As you can see, there are four ideal diodes A, B, C, and D, and they are connected in diamond shape. And this kind of setup we call is a bridge rectifier circuit, and a resistor is also connected, and the resistance of resistor is given. That resistance is equal to 2.4 kilo ohms. We will need this resistance later. What we need to answer, we need to just mark the letter P for the positive terminal of the load on figure 11.1. Positive terminal. Positive terminal of the load simply means that current entering side is a simple way to understand this one. Current entering side is positive terminal. Current entering side. Now we need to find out from which side current will enter. It will enter from top to bottom or bottom to top. This is what we need to find with the help of this power supply. So when this side is positive, means current flow from this power supply in this direction. At this junction, it has two options to go through A or B, but it will go through A because this is connected in forward bias. Again, at this junction, it has two options to pass through D or pass through this wire. It will go through this wire because this wire has no resistance, and this diode is connected in reverse bias. From here we can see current will enter from bottom to top, so it means the bottom side has to be positive, or simply we will write here letter P. We have to mark P here. And then current will go this way. When it will reach at this point, it has two options. These two diodes are connected in forward bias, mean it can go through B or it can go through C, but it will only pass through C because B, this side is at higher potential as compared with this side. So that's the reason it will not go through B, because current always flow from higher potential to lower potential. So it will go to lower potential side in this direction and come back to power supply. So this is the case when this is positive terminal. We also need to understand the second case when the lower side is positive. Means when this side become positive, so current will flow this way. Current will enter and then current will go like this. At this point, it will pass through D and then current will flow like this. Again, it will enter from the bottom, and when it will reach at this point, it has two options to pass through C or B, but in this case it will pass through B because C other end is at higher potential. Because this is at higher potential, this is at lower potential, so it will go to this side. It will pass through B. Means current always flow from higher potential to lower potential, means for high value of V to low value of V. So this is very important concept. So this is how we can mark, and that's all for this part. For part B, potential difference against time graph is given to us. As you can see, time is on x-axis and potential difference is on y-axis. We simply need to calculate RMS value of current for the load. So how we can calculate, because in this case we don't have the peak value of current, only we have is the potential, and also we have value of resistance. So how we can answer this question? So first of all, we need to find RMS value of potential difference. Simply we can calculate like this, means we need to find VRMS, and VRMS simply we can find by V peak, means the peak value of voltage. We just need to divide by 2, so we can get VRMS, and when we have VRMS, then we can find out IRMS. That will be equal to VRMS divided by simply resistance. So this is the main concept, or we can say these are the main steps we need. Remaining is just plug in values. So here you can see the solution I have written for you. So first of all, we have calculated VRMS, because the V peak we can just read from here, in this case is 6 volts. So we got VRMS. Now here we can find IRMS. Simply we need to divide VRMS by resistance, and the resistance is given to us. This resistance, as you can see, this is the value of resistance. We just simply divide it, and here is our final answer. For part B, simply we need to sketch on figure 1. For C1, we just need to draw the symbol for a capacitor to produce smoothing. For C2, the minimum potential difference across the load L with smoothing capacitor is 3 volts. And also again on figure 11.2, in this case this is figure 11.2, we need to sketch the variation with time t of the potential difference across the load L. So it means we have to sketch 2 times. So to answer this question, the first thing what we need to understand is that minimum potential difference is given to us. Minimum potential difference is given across the load. So it means the minimum potential, first thing we can say that V minimum across the load is 3.0 volts. So this is one thing. The second thing we need to understand, as it is a bridge rectifier circuit, this is bridge rectifier circuit, so output is a full wave rectification. Bridge rectifier, so the output is full wave rectification, means only we will get positive value of current. Full wave rectification. So this is very important point. Often students, they get confused what to do with this one, because this question is all about bridge rectifier. So bridge rectifier, full wave rectification. So based on these points, we can answer this question. So this is how I have drawn circuit for you. Actually, this is C2. This is not C1. If you can look at this one now, you can see, first of all, this was given to us without rectification. Then when we rectify this one, this is what we will get. After rectification, this is what we will get. So this is full wave rectification. So this is what we're gonna get after rectification. So this is after rectification. So this is what we will get after rectification. So simply we need to understand the negative become positive, so current only flows in one direction. The second curve you can see here, I have drawn here. So this is due to capacitor. So you can see at this point, this is the minimum potential difference, and this is 3.0 volts, and the same is true for this one. So we have to be clear about this. It has to be 3.0, otherwise you will lose marks. Again, you can see here current will decrease decrease here. So a potential difference actually, a decrease, and this is 3.0. Again, at this point, you can see the potential difference here is 3.0. So this is how we need to draw this one. I hope it is clear to you. Let me show you C1 as well. For C1, simply this is what we need to draw, the symbol for a capacitor. Symbol for a capacitor. So here is our symbol. So this is what you need to draw, and this is our answer for C1. Welcome to A-Level and AP Physics, a place where you can improve your understanding of physics with confidence. In today's lesson, we will talk about AC and rectification from Cambridge A2 Physics. This is our 5th video on this topic. In today's class, we will explore about bridge rectifier circuit, a special case of bridge rectifier circuit when diodes are not arranged in diamond shape. For this question, a bridge rectifier circuit is given to us, and there are 4 ideal diodes, and also we can see here are 4 diodes, and we can see how they are connected. So these are 4 given diodes, and this is how they are connected. If you look at the shape of this arrangement, it doesn't look like a diamond. So this is not a typical shape of bridge rectifier circuit, but it is still bridge rectifier circuit. What else is given to us? An alternating power supply is connected between A and B, and also the RMS value of EMF is given, that is equal to 7 volts. For part A1, we simply need to circle the diodes that conduct when point B is positive with respect to point A on figure 10.1. Let's try to answer this one first of all. So to answer this question is a very simple principle, as it is given to us that B is positive with respect to B, with respect to A. So we can just use this positive sign here. So B is positive. So when the B is positive, simply we understand if we have DC power supply like this, so current will flow from positive to negative, means when this is positive, current will flow in this direction. So same is true here. So current will flow from B to this side. When it will reach at this point, it has 2 options to go. So this one is in reverse bias and this one is in forward bias. So current will go this way, it will not pass through this one because this is connected in reverse biased. So current will pass through this one. After passing through this diode, when current will reach at this point, again it has 2 options to go up or go down. But if current will go down because this one is in reverse biased. So R I'm using for reverse bias, means when reverse bias. So in this case, the resistance of diode is infinite, means current does not flow. So the resistance is infinite. We are talking about ideal diodes. So again, so current will flow in this direction. It will pass through this resistor, and after passing through, current will reach at this point. So again, at this point, current has 2 options. It can pass through this diode or it can pass through this one. But it will pass through this diode. The reason is that because this diode, this side is connected with positive terminal of the battery and this side is connected with negative. So it means this side is a high voltage, this side is low voltage. Current only flows from high to low, not low to high. So this side is low voltage. So this is low, L for low. So that's reason current will not flow through this diode. So current will flow like this. So this is how you can see how current will flow in this given setup. So only diodes, these 2 diodes will conduct So this is one diode we need to circle, and the second diode is this one. This will also conduct. So this is our final answer for part A1. Let's move on to part A2. For part A2, simply we need to find the maximum potential difference across a resistor. It also simply means that Vmax, we can also say, is equal to V peak, means the maximum value of potential difference. And this is equal to root of 2 times Vrms. In this case, Vrms is given to us. This is value of Vrms. Simply we can plug in value of Vrms. If we just multiply this one, we will get our final answer, that is equal to 9.9 volts. So this is our final answer up to 2SF. For part B, potential difference is given on y-axis and time is given on x-axis. We can also find the magnitude of ripples from here, or you can simply see the magnitude of ripples. You can see magnitude is big or magnitude is small from here. And it is also given to us that a capacitor is connected into the circuit to produce smoothing of the potential difference across a resistor. This is very important point, across resistor. For B1, we simply need to draw the symbol for capacitor connected so as to produce smoothing on figure 10.1. So as you can see here, draw the symbol for capacitor, and we need to produce smoothing of the potential difference across resistor R. It simply means that our capacitor also has to be connected across resistor. Across resistor, simply we need to connect capacitor. Otherwise, a simple way to understand this one is, as this is a bridge rectifier circuit, so simply you can remember also like this. As this is a bridge rectifier circuit, we need to connect capacitor across load. Bridge rectifier circuit. For this one, our capacitor. So I will just write down here, our capacitor has to be connected in parallel with load. Capacitor connected in parallel with load. Load in this case simply means resistor. In parallel. So we simply need to connect capacitor in parallel with this resistor. So this is how we can connect capacitor across resistor R. So it means connect capacitor parallel. So capacitor in parallel. So you can also understand from here, capacitor has to be in parallel. So this is the main concept what you need to understand. Next part is B2, and for B2 simply we need to state the effect, if any, on the magnitude of the ripples on V when separately. It means we just make one change at a time. Very important point to understand. So the first change is we change the capacitance of capacitor. We use a larger capacitor, means with larger capacitor. So what is the effect of that one on magnitude of ripples? As you can see here, magnitude of ripples we can find from here. In order to answer this question, we need to understand one more simple concept about capacitor, that is called tau, means the time constant, and time constant depends on resistance and capacitance. If we increase the capacitance of a capacitor, its time constant also increases. Tau is the time constant. Tau is the time constant. So as C increase, means the capacitance increase, tau will also increase. So simply we will say it will discharge slowly. We can also say in this case capacitor will discharge slowly. When the capacitor will discharge slowly, we can also see from here, discharge slowly means that its potential difference will decrease slowly. So here you will see its potential difference maybe will be this. So now if you look at the ripple, the magnitude of ripples is only this much. So it means if we use a large capacitors, the magnitude of ripples decreases. So this is our final answer. This is how we can answer this one. And so simply what you need to write down is, you need to simply say ripples decreases That's all what you need to write. You no need to explain anything. But I have also written for you this explanation because capacitor discharge slowly. Next part. The next thing is asking us if the resistance is smaller, mean the resistance of the circuit, if we decrease, what is effect on time constant? First of all, we will see effect on time constant, and then we will see the effect on magnitude of ripples. So now from here we can see if we decrease the resistance. So I will rewrite this one. Tau is equal to RC. In this case we are not changing C because it is given to us very clearly. We have to take one change at a time. So in this case we keep C constant. Now we change resistance. In the previous case we kept resistance constant. Now if we decrease resistance, simply we will say the time constant will decrease, means the time taken for a capacitor to discharge 63% of its initial value, or simply at this point you can simply remember is the time taken. Time taken will decrease, it means it will discharge quickly. So we will say capacitor will discharge quickly. So this is, it will discharge quickly. Discharge quickly means that its potential will even go, potential difference across capacitor will even go lower than this value. We can sketch something like this. So you see increases. So we will simply say ripples increases. Ripple increases because capacitor discharge quickly. Here is our answer. This is what you need to write. For the sake of this question, you can only write down ripples increases. So if you only write this much, you will get 1 mark. This is.